Welcome. Today we're taking an in-depth look at the world of software design patterns. Our main source is the book Dive into Design Patterns, which is a great resource for developers wanting to build better systems. Our goal here is to pull out the key ideas and insights for you, giving you a solid understanding of this important topic.
It's certainly a broad subject, and this review, it's worth noting, has been generated by AI. This ensures an objective summary tailored for a technical audience like yourselves. After our discussion, we do suggest reading the full book. It really gives a complete picture and a deeper dive into all these concepts.
A very good point. So let's begin with the fundamentals, how objects are structured and interact. We'll assume you have a grasp of objects, classes, inheritance. But let's quickly touch on three concepts patterns really depend on: abstraction, encapsulation, and polymorphism.
Precisely. Abstraction is about modeling things from the real world in code. But, crucially, only showing the details relevant to the current problem. Think about an airplane class. In a flight simulator, you need lots of detail, like aerodynamics. But for booking flights, you only need things like capacity and flight routes. You hide the rest.
And closely related is encapsulation, or information hiding. This means keeping the internal state and workings of an object private. You only expose what's necessary through its public methods, its interface. Now, that word interface can be a bit confusing.
They can, because besides being the public part of any object, it's also a specific type in many languages, defined with keywords like interface or protocol. These define a contract. They specify methods an object must implement. This allows objects to work together predictably without needing to know the specific internal details of each other.
Like having a flying transport interface with maybe a fly method. An airport could then work with anything implementing that contract. An airplane, a helicopter, maybe even a domesticated griffin if it implements fly.
Exactly, and that leads us right into polymorphism. Let's stick with animals. An animal superclass might have an abstract method called makeSound. This forces subclasses like cat or dog to provide their own version. Meow or woof. Now, imagine you have a list containing different animal objects.
Just a mix of cats and dogs.
A mix. And you loop through this list, calling animal.makeSound on each one, even though your code might only see them as generic animal types. The program is smart enough to run the correct sound method for each object. The cat meows, the dog barks. That's polymorphism.
So the program figures out the object's real type at runtime and calls the right method. That's how an object can act like its parent class or an interface it implements.
Precisely. It allows for very flexible and dynamic behavior.
Okay, that sets the stage nicely. Understanding these behaviors requires understanding object relationships too. We have association, where objects use each other, often a lasting link, like a professor object knowing its student objects.
Then there's dependency, a looser link. If a professor's teach method needs a course object passed to it, the professor depends on the course. Changes to course could affect the professor.
And we get more specific with aggregation and composition. Aggregation is like a whole-part relationship. A department has professors, but the professors could exist without the department.
Whereas composition is stronger, consists of. Think of a house and its walls. The walls are part of the house, managed by it. If the house is destroyed, the walls go with it. They can't exist independently.
And of course, there's inheritance, the is-e relationship, where a subclass gets features from a superclass. All these relationships define how we structure our code. Which brings us to design patterns. What exactly are they, in simple terms?
Think of them as standard solutions to common problems you encounter when designing software. They aren't specific code snippets you just copy. They're more like general concepts or blueprints. You adapt them to your situation.
So not like an algorithm with exact steps.
Yeah. No, more like a strategy or proven approach. The idea actually came from architecture first, describing patterns in building design. It was later applied to software development, notably in a very influential book published back in 1994.
And why should developers put in the effort to learn these patterns?
Well, several reasons. First, they represent a toolkit of solutions that are known to work. They've been tested. Second, learning patterns helps you understand object-oriented design principles more deeply. You learn how to solve problems in a structured, flexible way.
And there's the communication aspect too, right?
A huge benefit. Patterns provide a shared vocabulary. If you tell your team, let's use a singleton here, everyone understands the structure and intent immediately. It makes technical discussions much more efficient.
That makes sense. So before we look at specific patterns, maybe we should touch on some core software design principles. These are like guidelines for good architecture.
Good idea. A key goal is always reusability. Writing code that can be used again easily. Frameworks, like testing frameworks, represent a high level of reuse. They dictate structure. Patterns are kind of in the middle. They describe how a few classes work together, offering reuse of design ideas, perhaps with less commitment than a full framework.
And another critical goal is extensibility, making software easy to change or add to later.
Absolutely. Requirements change, understanding improves, technology shifts, change is constant. Good design anticipates this. It plans for future modifications.
Which leads us to principles like the single responsibility principle, or SRP.
Yes, SRP states that a class should have only one reason to change. Imagine an order class. If it handles both placing the order and calculating sales tax, it has two reasons to change: if order logic changes or if tax rules change.
So SRP suggests separating those.
Exactly. Move the tax calculation into its own dedicated class, say tax calculator. Now the order class only changes if order logic evolves, and tax calculator only changes if tax rules evolve. Each class has a single, focused responsibility.
Makes the code easier to manage. What about depending on abstractions?
That's the dependence inversion principle, or DIP. Depend on abstractions, not on concrete classes. You often hear it as program to an interface, not an implementation. Instead of your high-level company code directly using junior developer and senior developer classes,
You create an employee interface.
precisely. The company class then only interacts with objects through the employee interface. It doesn't know or care about the specific concrete types like junior developer. This makes it easy to add new types, like lead architect, without ever changing the company class. It increases flexibility dramatically.
That sounds powerful. It relates to another principle: favor composition over inheritance.
It does. Inheritance seems like the obvious way to reuse code, but it creates tight coupling. Changes in the parent class can easily break child classes. And if you need to combine features from different dimensions, like color and engine type for a vehicle, inheritance can lead to a confusing explosion of subclasses. Red gas car, blue electric truck, and so on.
So composition's preferred.
Often, yes. Instead of a car being a red gas car, a car object has a color object set to red and has an engine object, a gas engine. You can change the color or engine by swapping these component objects, maybe even at runtime. It's usually much more flexible than a rigid inheritance structure.
And this flexibility helps with the open-close principle, OCP.
Definitely. OCP says classes should be open for extension, but closed for modification. Once a class works and is tested, you ideally shouldn't change its source code to add new behavior. Instead, you extend it, either through inheritance, subclassing, or, often better, using composition.
Like the shipping example. Instead of editing the order class for express shipping,
You extract the shipping logic into separate shipping strategy classes. The order class holds a reference to a shipping interface. To add drone shipping, you just create a new drone shipping strategy class. The order class remains untouched, closed for modification, but open to new strategies.
Okay. And there are a couple of others worth a quick mention.
Yes, the Lysakov substitution principle, LSP. Basically, if you have code that works with a base class object, it should also work correctly if you give it an object of any subclass without knowing it's a subclass. Subclasses must be compatible substitutes. And the interface segregation principle, ISP. Don't force clients to depend on methods they don't use. Keep interfaces small and focused on specific roles. Avoid fat interfaces.
Great overview of the principles. Now let's look at some actual patterns, starting with creational patterns. These deal with how objects get created. First up, factory method.
The core problem factor method addresses is when you want to create objects but you don't know the exact concrete class up front. Or you want to let subclasses decide which specific class to instantiate. Imagine a logistics application. Initially, it only creates truck objects using new truck.
But then you need to add ship transport.
Right. Now you have to find all new truck calls and add conditional logic, maybe new truck, else new ship. It gets messy. The factory method solution is to define a method in a superclass, say create transport. Subclasses like road logistics and sea logistics then override this method. Road logistics.createTransport returns a new truck. Sea logistics.createTransport returns a new ship.
So the client code just calls logistics.createTransport and gets the right object.
Exactly. The client works with the transport interface, and the concrete creator subclass handles the specific instantiation. It decouples the client from the concrete product classes.
Okay, another very common creational pattern is singleton.
Singleton tackles two things, actually. First, ensuring a class has only one single instance. Useful for things like a database connection pool or a configuration manager where you need exactly one. Second, providing a global point of access to that single instance.
How does it enforce the single instance rule?
The key is making the class's constructor private. This prevents anyone outside the class from just creating new instances with new. Then you provide a public static method, often called getInstance.
And getInstance controls the creation.
Yes. The first time getInstance is called, it creates the single instance and stores it in a private static field. Every subsequent time getInstance is called, it simply returns that already existing cached instance. This ensures only one object is ever created. It's often done using lazy initialization. The instance is only created when first needed.
Simple concept, but sometimes controversial.
It can be. While useful, some argue it violates the single responsibility principle because it controls its own creation and provides its core logic. It can also make testing harder and potentially hide dependencies if overused. It's a tool to use carefully.
Good to keep in mind. What about the other creational patterns, briefly?
Well, Abstract Factory is like a step up from Factor method. It helps you create families of related objects. Imagine creating UI elements. An Abstract Factory might define methods like create button and create checkbox. Then you'd have Windows Factory and Mac Factory concrete factories, each creating buttons and checkboxes that look right for their respective OS.
So it ensures consistency within a family of products.
Precisely. Then there's Builder. This one is great for constructing complex objects step by step, especially if the object has many optional configuration parameters. Instead of having a massive constructor with tons of arguments, the Builder lets you set properties individually and then build the final object. It separates construction from representation.
Useful for things like complex configuration objects or, say, building a pizza with different toppings.
Good analogy. And finally, Prototype. This pattern lets you create new objects by copying an existing object, known as a prototype. You don't need to know the concrete class of the object you're copying. The objects themselves know how to clone themselves. It's useful when object creation is expensive or you need copies of pre-configured objects.
Okay, that covers creational patterns. Let's move to structural patterns. These focus on how classes and objects are composed into larger structures. How about the adapter pattern first?
Adapter is all about making incompatible interfaces work together. It acts as a translator or bridge. Imagine you have a component that expects data in a specific format, maybe using specific method names. But you have another component or library that provides the data you need, just with a different interface, different method names, different structure.
And you can't change the library.
Yeah, right. Maybe it's third-party code. So you create an adapter class. This adapter implements the interface your first component expects. Internally, it holds a reference to the incompatible component, the adaptee. When your component calls a method on the adapter translates that call into the appropriate calls on the adaptee.
Like a travel power adapter lets your US plug fit into a European socket.
Exactly that. It adapts one interface to another.
Now, how does that compare to the decorator pattern? It also seems to involve wrapping objects.
That's a common point of confusion. Both involve wrappers, but their intent is different. Adapter changes an object's interface to match what a client expects. Decorator, on the other hand, adds responsibilities or behaviors to an object dynamically, without changing its interface.
So decorator enhances an object while keeping the interface the same.
Precisely. Think about adding features like scrolling or borders to a text view component. Or consider a notification system. You might have a basic email notifier. Then you could create SMS notifier decorator and Slack notifier decorator. These decorators also implement the notifier interface. You can wrap the original email notifier with an SM notifier decorator and then maybe wrap that with a Slack notifier decorator.
And the result sends email, SMS, and Slack messages.
Correct. You stack decorators to combine behaviors. It avoids the subclass explosion you'd get trying to represent all combinations. Email and X notifier, email and Slack notifier, email and Slack notifier, using inheritance. It's very flexible for adding optional features.
Okay, that distinction is clear. Can we quickly touch on the other structural patterns?
Sure. Bridge is about decoupling an abstraction from its implementation so they can vary independently. Think of separating a remote control abstraction from the specific device implementation, TV, radio. Composite lets you compose objects into tree structures and then treat individual objects and compositions uniformly. Useful for graphics or UI hierarchies. Facade provides a simplified, unified interface to a more complex subsystem. like a single video converter class, hiding the complexities of various audio-video codecs and processing steps.
Hides the messy details.
Exactly. Flyweight is a memory optimization pattern. It lets you share common parts of object state between multiple objects to reduce memory usage. Useful for things like characters in a text editor or particles in a game. And proxy provides a surrogate or placeholder for another object to control access to it. This can be for lazy initialization, access control, logging, or representing remote objects.
It sounds like proxy also uses wrapping, like adapter and decorator.
It does, but again, the intent differs. Proxy controls access and often manages the life cycle of the real object, whereas decorator adds behavior and adapter converts the interface. The proxy typically has the same interface as the real object it represents.
Got it. Well, let's move to the final group, behavioral design patterns. These deal with algorithms and communication between objects. How about the strategy pattern?
Strategy is about defining a family of algorithms, encapsulating each one, and making them interchangeable. It lets the algorithm vary independently from the clients that use it. Think of a sorting algorithm. You might have quick sort, merge sort, bubble sort.
Different ways to achieve the same goal, sorting data.
Exactly. Or route planning in a map application. Driving strategy, walking strategy, public transport strategy. The strategy pattern suggests putting each of these algorithms into its own separate class, all implementing a common strategy interface, e.g. an execute or sort or plan route method. The main class, the context, like the sorter or navigator, holds a reference to one of these strategy objects.
And delegates the actual work to the strategy object.
Precisely. The context doesn't implement the algorithms itself, it just calls the execute method on its current strategy object. The client code usually decides which concrete strategy to provide to the context. This means you can switch strategies easily, even at runtime.
Very flexible. How does that compare to, say, the state pattern? State also seems to change an object's behavior.
Another good comparison. State lets an object alter its behavior when its internal state changes. It appears as if the object changed its class. Think of a document object. Its savior behavior might differ depending on whether its state is draft, moderation, or published. Like strategy, state often uses composition, delegating behavior to separate state objects.
So what's the key difference from strategy?
The main difference is often intent and how transitions happen. Strategy usually involves interchangeable algorithms chosen by the client. State typically represents the internal condition of the context object itself, and the state objects themselves often handle transitions to other states. For instance, the draft state object's publish method might change the document state to moderation state. Strategies usually don't know about each other.
Okay, that makes sense. Let's talk about observer.
Observer defines a one-to-many dependency between objects. When one object, the subject or publisher, changes state, all its dependents, observers or subscribers, are notified and updated automatically. Think of a spreadsheet. When you change a cell's value, the subject.
Any charts or formulas that depend on that cell, the observers need to update.
Exactly. The cell doesn't need to know the specifics of the charts or formulas. It just maintains a list of observers. When its value changes, it loops through its list and calls an update method on each observer. This creates a loose coupling. The subject knows that it has observers, but not who they are specifically, beyond them implementing the observer interface.
Used a lot in event handling systems.
Very common there, yes. It allows objects to react to events without being tightly bound to the event source.
Okay, let's quickly round up the other behavioral patterns.
Right. Chain of responsibility creates a chain of processing objects for a request. Each object decides either to process the request or pass it to the next object in the chain. Useful for handling events in a UI hierarchy, for example. Command turns a request into a standalone object that contains all information about the request. This lets you parameterize methods with different requests, queue or log requests, and support undoable operations.
Underrated was a classic use case for command.
It is. Iterator provides a way to access the elements of an aggregate object, like a list or tree, sequentially, without exposing its underlying representation. It separates traversal logic from the collection. Mediator promotes loose coupling by encapsulating how a set of objects interact. Instead of objects referring to each other directly, they only talk to the mediator, which directs the interactions. Good for complex UI dialogues.
Stop objects getting tangled up with each other.
Precisely. Memento allows you to capture and externalize an object's internal state so the object can be restored to this state later without violating encapsulation, essential for implementing undo or transactions. Template method defines the skeleton of an algorithm in a superclass, but lets subclasses override specific steps without changing the algorithm's overall structure. It uses inheritance to customize parts of an algorithm.
So it defines the overall flow, but lets subclasses fill in some details.
Correct. And finally, visitor. This pattern lets you define a new operation for an entire class hierarchy without changing the classes themselves. It works by having the visitor object traverse the object structure like a tree. Each element in the structure accepts the visitor, essentially telling the visitor, I'm a circle, or I'm a square, allowing the visitor to perform the right operation for that specific type. Useful for adding operations like export to XML to a set of existing classes.
We've certainly covered a wide range of patterns today. It shows how powerful and elegant these established solutions can be for developers.
They truly are a fundamental part of a software developer's toolkit. Understanding them is essential. It helps you create software that's not just functional, but also flexible, easier to maintain, and reusable. And, as we mentioned, it provides that common language which is so valuable for team collaboration.
This has been a really insightful exploration based on the concepts and dive into design patterns.
And as a reminder, we do recommend reading the full book itself. It will definitely deepen your understanding and show you more practical ways to apply these vital design concepts.
Definitely worthwhile. And here's something to think about as we close. These design patterns, while technical and abstract, often reflect broader problem-solving approaches we see everywhere, not just in code. How might recognizing similar patterns of structure, behavior, creation, and other complex systems influence how you approach challenges in general? Thank you for joining us today. We hope this discussion has been valuable for you.